So any questions on the lab that we're working on now? What we're trying to do is just make this little robot, come up with the specifications, what were some of the specifications we came up with.
Degrees of
Freedom? Y'all, first of all, y'all did payload, right? Have y'all done that yet?
no,
We
we
load it
didn't
back.
get to that.
We get the little sling and start putting batteries on there to install the robot. Another one we're dealing with is speed. How fast can you move the thing, right? How fast can you move the axis, anything else? And some of y'all are working on the actual envelope. So we have some paper I put out here. Tyler is always working on here. And basically, we'll just put some paper together. Looks like what 6 by 6, 3 by 3. I'm sorry, not 6 by 6. 3 by 3. And then you set the robot on the floor, right? Stand and make it go around. And then you take the wall over here. You got to do both. Do the envelope. You got to do the rotary and the lid. You understand that? So I'll put a plain paper out here for that. What I don't know what else. After that, what we're going to do is we're going to actually do online programming with the robot. And only for some reason that I hadn't been able to figure out, only a certain number of computers will run this. So y'all are going to have to give up your computer to another group, or your group's going to have to go to the computer. But if you look down on the doors, you'll see some of the computers have got these little yellow tabs on there. Those are the computer that has the ability to run the robot. Down on the door where you access the CPU. Got a little yellow tab on it. And what we're going to do is we're going to do online programming. And what we have to do is first of all, is we have to connect to the computer. So the computer is going to be the controller. Okay. So what we do is we disconnect the pin. That's how the teach. That's just a manual job. What we have to do, and then we hook up a printed circuit board to the computer. It runs off the IEEE 488 interface. That might be something y'all can use a lot. This is the old parallel port. This has disappeared from the computer. So we get this card. They're in the box with the slings and the manual pin. Make sure you turn it off when you plug it in, or your robot will take off. And then once you get the application running, you can turn it on. Y'all don't need to do this. It gives y'all really good directions in the lab. But to find the application, let me go ahead. But to find the application, you would go to Start. Oh, by the way, a couple of things we got to get used to doing in the lab. Number one is everybody, when you leave here, there was a few machines that was left logged on. So if you're by chance checking your grades on Blackboard or stuff like that, and you don't log these computers off, you just get up and leave. Then what happens is the next person that comes in and sits down, since we use a generic account, so everybody uses METSTU, right? Welcome. Then when they load it up, everything that you had open is still going to be open. So on Windows XP, to log off, you just click on the Start, and then right down here it says log off. Now when you log the computer off, what it will do is it will shut down everything that you had running. And then the next student that comes in and logs in, it'll be a fresh login. So y'all need to get used to doing that before y'all leave here. Another thing we need to get used to doing before we leave here is pushing all the keyboard trays in and pushing these chairs back under. This is one of the show and tell classrooms of the college. A lot of people that come in here, they come into this classroom for obvious breathing. So this is one of those. This in the lab next door. The two most high-tech probably places that we have on this campus. So it's shown off a lot. So what we can do when we log y'all in, we have our own domain server here at the college, and what it allows us to do is do things for you. One thing, if you go to my computer, when mine logs up, when mine shows y'all, everybody should have a map drive that says my students. We'll call it the Z drive down here. This will have a lot of information out here that you'll use while you move through the program. Now you can't access this from the library computer because this is our domain. And then you'll go to robotics, and then y'all are in intro to robotics. These are the two things that we'll deal with. When we learn how to program the Heath robot, this is where you go in and get the syntax for all the commands. This will be the one you go into, and this will be the program that you're going to run right here. This how we incorporate. And like I said, that's laid out. And when you do that, this screen right here is going to pop up on here, and this is where we can actually program the robot. Of course, it gives you the 5 axes that's available. And then you just come up here. If you want to move the base clockwise, then you just see now the robot is, we're not using the T-spin anymore, we're actually moving the robot. And what this does, this is an open loop robot. So one of the methods we program an open loop robot, we use hard stops or variable hard stops, or we use time. And this application uses time. So what it did was just recorded the time that I ran those axes. When I come up here and execute it, so it's imperative that you get the base back where it was at. So I don't know exactly where it's at. So you probably need to put a line on the robot or something, because where you want to do to make your program repeatable, what you want to do is that when you finish it, you want to put it back where it was at when you started. That makes sense. So that way you can run it multiple times. And then when you get through, you just hit execute, and then the robot runs its program. So this is teaching, right? You understand. So what we're doing is we're taking the robot through a set of moves, and then when we execute the program, it does what? It repeats those moves. So right now, you're jogging the robot with that manual pendant. It's not a T-pendant because we can't do online. This is online programming. If it was offline programming, I would complete the program completely on a computer, and then I would upload it into the robot. But here we're actually, as soon as I come up here and hit these keys, the robot moves. So here our computer that we're sitting at is serving as the controller. And this is my teach pendant right now. This is it. This is the teach pendant. So there's the parts. We have the controller, we have the teach pendant, and we've got the robot, right? And of course we got the power supply. You can clear the whole program right here. You can put what I usually do is, to make it real easy to find, is I run the robot until it hits its hard stops. Because these guys have got slip clutches on it. So basically what I would do, this has got bad gears in it. Let me turn this off. This is one of the bad ones somebody brought over here. I don't use these right here in front. So as I turn the interface board off, it's got a little switch on there that says on off. It's pretty straightforward. So what I usually do is I put the robot against its hard stop. And then from then on, it's a fairly easy program. So let me turn the board back on. And y'all look, these guys, it's got slip clutches on it. So slip clutches mean that when you hit the hard stop, it's not going, the motors are not going to stall. The clutches are going to start slipping. Then when I get against this hard stops, so notice I'm letting it run too long, right? And then what would I do? Now, if I return the robot to this position at the end of my program, then I can keep running the program over and over. I'll understand that. Because if you put it in this real strange position that's hard to find, you don't bring it back to that exact position, then the next time it runs it, everything's going to be off. I understand what I'm saying. Now we can teach the robot. You can clear this. There's things you can do though. So I'm gonna clear the whole program, and then now we can come up here and we can teach the robot. So I had it up against the hard stop, right? You understand that? And all I'm gonna do at the end is just do run it past this hard stop. You understand? Yes or no?
How do you do that?
You just keep jogging. So see, I'm swinging around like this. Well, if I was to leave it right there and then run the program and then I run it again, it don't know it's out there in the center, right? You understand? But if I was to take this now and turn it back up and run it back long enough till it hits its hard stop, right? You understand? And then let it run for a little while. It don't hurt it because it just slips, right? It's got slip clutches. So I'm returning it back to where it was at. Now here it comes. It's going to hit. So I started at the hard stop. Now it's up against the hard stop and it's slipping. I'm going to leave it there. So now I can come up here and I can execute it. And then when it gets out here, it does what I want it to do. It's going to do what? It's going to return back to where it was at, and now I can run this program over and over and over again, and it'll do the same thing, even when the batteries start running. How many power sources are there for robot? No. Pneumatic, hydraulic, electric.
And then they articulated?
Yeah, articulated is not a power source. Articulated just means the robot is jointed. Usually two or more joints. I didn't mark any points. I just did it. I just ran it the way I wanted to run. What do you mean mark the points? This is my start point and my end point. What you want to do is you want your start point and your end point to be the same. If your start point and your end point are not the same, then you're going to have problems with repeatability, right? You understand? Without I don't know what you mean. I ran it for a certain amount of time. So this is an open loop robot. So open loop robots, we either have to depend on hard stops or we're going to run the motors for a certain amount of time. Open loop means what?
Servo.
Means non-servo. What does non-servo mean? That's what I'm asking. What does that mean? Huh?
Manually operated prototype.
Doesn't mean it's not. Doesn't mean it can't be manually operated. It means there is no feedback. So this is like me having a light switch on the wall over here that controls the light in the men's room. That's open loop. So I go over and flip it up on. I have no idea it's on because there is no feedback. Now, of course, in here I can go over there and I can turn that light switch off, and I have feedback. What's my feedback? My eyes is the feedback. The light bulb is not the feedback. The light bulb is the actuator, right? You understand that? Feedback means there's some method I know when I tell an actuator to do something, I know that it's done. And those are servo systems, or what we call closed loop systems. Open loop system. Now you got to understand this computer has no eyes. So I can see it move. Right? You understand. But the computer can. So what does it use? It's open loop. It's using hard stuff.
Hard stuff and you.
Well, no. When I run the program, the computer is not it cannot see. I can see. So I can say, okay, I want to jog it over here. I can pick up that block. I can come over here and move it up, and I can do that. I can teach it. I'm looking at it. It's just like over here when you teach these robots, you're looking at the robot, right? Understand? But when you hit teach over there, that controller records the position because it's a closed loop robot. Over here, when I run that program, it cannot see, right? You understand? So how does it know when to run the motors? How does it know when to stop the motor? Not when I tell it to. I'm running the program.
The time.
It's time. It's time. So what we do is notice up here, it says I'm going to move this base. I'm going to move it counterclockwise for 14.38 seconds. That's what the controller knows. The controller does not know the position of the robot. All it knows is I'm running it 14.38 seconds.
So initially you would run it how you want it to run once the program.
Yeah, it's just like over there. When I teach that robot, I'm manually moving the robot and I'm looking at the robot to see what it does.
Would you ever, I guess there is where you would just put in a number, a time, or do you just run it to test?
Well, if you put in a time, you're going to have to know the exact speed of the robot. You're going to have to know the exact speed of every axis. These axes are not geared the same. So that means if I run one axis for 15 seconds and I run the gripper for 15 seconds, it's going to be different depending on how the motor's geared. So you'd have to keep up with the speed of everything. Now over there, we can key in numbers. It's hard to do on the robot. It's really easy to do on the simulation. So over here, that robot has feedback. So I can say drop that gripper down 180 degrees. And by George, it's going to come down exactly what? Because the controller gets feedback from the actuator. So understand that. And so how did it know? Well, I'm up against my hard stop again. So I'm going to clear my program, so I can clear my program. And then I'm saying, okay, I want to spin this thing around. Well, what I'm doing is I'm coming over here and I'm spinning the base. Right? You understand that?
You have to spin it first, but the machine tells itself.
Yeah, well, right now, I'm holding down counterclockwise. And I'm on a robot, I'm going to move this thing where I want to move it. And then when I get it to where I want it to be, right, you understand, I'm going to stop. Now, as soon as I did that, it recorded which axis I moved, and it recorded what? The amount of time I ran. And the direction. So here, if we take the shoulder down, supposedly
Automatically, that puts it in second.
It's going to drop down to the second move. Now, if I put it back to a known position, then we can clear the point. We can remove the point and then reteach. But notice it recorded that time.
So even though it's doing the same exact thing, because you stopped, it's starting to record time.
But as soon as I hit stop, it records the time. Now, it's no big deal if it says, well, I would need to bring it down a little more. If I want to bring it down a little more, it'll just record another move. See that? It just have two elements. And then, of course, when I get through, what do I need to do? Then let's open and close the gripper. And then when we get through, what would we do? Well, we'll just send everybody back. What I'm going to do is I'm going to send it back through the hard stop, right? You understand? So I'm going to let it slip. I'm going to let it slip. Okay, now notice now it hits against the hard stop. And I'm going to let it slip a little while. And then I can come up here and move the shoulder up.
There's not, okay. Do you have to program it to go back every time, or will it follow in the reverse pattern?
Well, that's what I'm doing. I'm giving it don't have.
Right, it won't do that on its own.
Yeah, you got to program it to go back. Yeah. Okay, then we need to. It's just like those robots over there. Those robots don't know anything. I mean, well, that's not true. Some of them, you can tell it in the teach mode. You can tell it to loop without programming it to loop, and that way it would work. But that's only some of these robots. So,
kind of a disadvantage of the open loop time.
Well, what happens is the time varies because this runs off battery, and the problem, and that's why I run it past where I want it to go. So here we can execute this, and it should do. But now I can run since I brought it back up against the hard stops and let it run for a second after that. Then it should be fairly repeatable. So I taught this program. You can see why it's called teaching, right? Because we manually moved the robot according to the path that we wanted to follow. And then when we run the program, it executes that path.
If it were closed loop, you could enter a program.
Well, what do you mean enter a program?
Like you could teach it without. Technology rather than moving it.
No, there's very few robots that you can type the program in and then let it run. Oh. Most of them, that's why it's called a teach vendor. So when you program these robots over here, when you do online programming, you're doing exactly what I'm doing here. Except one thing is that instead of recording the time, those controllers record the position. And then I go over there and I run the program. And over there, it's going to repeat it exactly. Over here is depending on time. This is an open loop robot. But if it's working okay, it should do what? It should go back to my original position, and I should be able to run the program over and over.
So every part.
No, this is open loop. Y'all are getting, this is a, open loop means this computer has no idea right now where this robot's at. No feedback. So what we do is we compensate for it. For one thing, what I did is I put the robot into a known position and I put it against its hard stop, right? You understand that? And I started my program with all the axes against their hard stop. So the gripper was closed, right? I was up against the hard stop back here for my base. Okay. Now this computer has no idea where that robot's at. Those computers over there knows exactly, they know where that robot is right now. Except for the ABB and the fan. The controller don't know what it is, huh? Those are all closed loop. What advantage does closed loop have over open? But that's not an advantage. What advantage does it have? That's not the advantage of closed loop. Your car has a closed loop system. What is your closed loop system? You got a cruise control on your car. That is closed loop, right? You understand? You have a closed loop system out there that runs your engine. That you used to, when you hit the gas pedal, it was the gas pedal. Now when you hit the gas pedal, it don't go to the gas. Where does it go? It goes to a computer called an engine control module. The engine control module is monitoring all these sensors out there, so it's getting feedback on your oxygen level, all this other kind of stuff before it decides how much air and how much fuel you get it. You got the cruise control. Cruise control, how hard it is for you to maintain a constant speed?
On cruise control?
No, when it's not off cruise.
It's hard.
It's hard. Yeah, you're constantly doing what? Adjusting the gas pedal, right? One minute you look down there, you're doing 90, and next minute you're going 60. You're on your cell phone. And everybody's blowing their horn at you. Right? You understand that? But when you engage that cruise control, you've got a closed loop system. So you're teaching it. Basically, when you hit that set, you just taught that thing what speed you want to run. And from then on, you can take the feet off the gas pedal, right? You understand? Right? You understand that? Yeah, and then you run into a truck. Don't know about that one. It was using the camera system, and they turned in front, and the truck had the truck back was all white, and the sky was cloudy, and the camera didn't see the difference between the two. Went right up to that truck. The truck was over, and you know what trucks have to do sometimes to make short turns, stop turn. Yeah, that. Nope. We had it on a lot. They find out a lot. That was one when it was actually, most of the wrecks on those automatic drive cars, Google's been testing them for years now. A couple of those have wrecked, but it's somebody else's fault. So it's basically unavoidable. This is the first one I know where the actual autopilot made them.
Those computers, I'm sorry, with the robot system that you showed us in the other room that picked up and it's fun and all. Are those are closed loop?
Every industrial robot that we have in our clinic. So that's why it's exactly the same thing. Huh? I give you all kinds of things. Every axis gives two types of feedback. It gives you position, gives the controller positional information, and also gives the controller speed information.
And that kind of lends to where when it dropped it and it stopped, it wasn't in the right position. The sensor sensed that the block wasn't in the right place and stopped. Mechanics were an open loop would just continue.
Oh yeah, an open loop don't know anything. It's you when you program. So usually a human programs an open loop system, right? You understand that? But then you turn it over to automatic control, and this is what I did. And this guy here has no idea. So I could come over here and grab this thing like this, and that controller has no idea. And now, when it runs it again, it does what? It's lost. Because it's open loop. Or what we call non-servo. Y'all gotta understand those two terms are used interchangeably. So what advantage does closed loop have over open loop? Closed loop, the controller knows, basically knows almost everything that's going on. What's the advantage of open loop? Cheaper. Open loop is cheaper. Because if I put a sensor out there, then I've got to have a portal into my controller that monitors it. And then I've got to add programming. I've got to program it. When I program it, I got to tell my program to monitor it. Right? You understand? Now we don't have to do it for the actual robot axis, because that's still the operating. But some programmer out there wrote the program that made the controller go out there and constantly monitor that right there. But if I want to open that gripper is an end-of-arm tool, and it wasn't on that robot, right? So they give me a set of portals that I can control, where I can say open this, close this, you'll get a feel of that. Hopefully, I need to pull out the robot for some of the things we're going to want you to do on the Hero robot is turn lights on, turn lights off, make it say stuff like that. Make it actually speak. The robot can speak to it. But it's something that you're going to have to put into your program, right? I don't understand. So since this is an open loop robot, we're depending on basically two things. We're depending on hard stops. So that's the way I put it in a known position. I just run it, I put it up against the hard stops to start it, right? So right now I started this and all the robot axes are at their wall, at their hard stop. So now when I run it, it's gonna do the same thing. And it's going to be pretty reliable because I started it from the hard side. And when I finished, I did what? I returned it to its hard side. We don't have to do that with those robots over there. So these robots, the ABB and the Big Fanic, the robot knows where it's at. But the controller's turned off, so the controller don't know where it's at. When I go out there and turn that controller on, the first thing it's going to say is, where are you at? And the robot says, I'm right here. And then from then on, the controller knows exactly where it's at. And not only does it know where it's at a point, it knows where the robot's at anywhere in its range. And we're talking about, nanometers. Those things, which basically smaller than the hair. So this guy here does pretty good, and now it's executing the program. But right now, if I was to come over here and grab this thing and not let it move, then what's going to happen?
You get lost.
It's lost. So next time I run my program, it's not going to do the same thing because why? So well, it don't know. So right now, so I'm going to hold this thing. Okay, you understand that? What does that say? Does it say anything? Don't look at the bottom. That's just showing you. I thought it adds. No, it didn't. It only adds stuff. Okay, so now it's supposed to be returning back to its home spot, right? You understand? Don't look at this right here. This is just the execution. And of course, now when I run it, it's going to be, the program has no idea what. Has no idea. Right. Good job. By the way, we don't very seldom do this. You can move points what? You can move them up, you can move them down. You can remove a point if you went in the wrong direction. So you wanted it to go clockwise and you send it counterclockwise. Instead of having the robot come up and do like this, you can just clear it, right?
Click on it and remove it.
Yeah. Usually when you screw up on this type of programming, normally you just put your robot back to the hard stops and then you just start over if you do it. So now I'm going to execute the program, and it's going to run the program. But now it's going to miss everything. Why is it going to miss everything? The computer has no idea that I jammed that thing up, so it don't know the position. So okay. So this is our first robot that we're going to teach. But you can actually see what teaching is, right? So teaching is when you take the robot through the moves you wanted to execute, and then once the program is taught, then you can cause the robot. There's really no command in this where you can cause it to loop. So now it's going to go down here and stall out. It's in trouble. Are you okay? So this is once you get with get through with the one you're working on now. This will be the next lab. The lab is called Remote Control. More precisely, it's online programming. Well, online means we do what?
Program it through your computer.
Well, you program it at the robot, at the control. And right now, this right here is what? Control. We'll get a fill offline program. The Lego robots are offline programs. You can online program. First thing you'll do when you build it is you'll do some online programming, and then you'll move over to offline programming. So now it's all messed up. Okay, any questions? Okay, we'll take the test at the end of class. So we're going to go lab. Oops, let's take it. Let me log off this computer so y'all can use it. All right, let's go lab. You're in lab. When you're in lab, it's your call.
So, the other day, not ready?
Yes.